Okay, so go ahead and get it written down, and then we will talk about it and break it down a little bit. Okay, and you can look at the lovely picture of the dancer and kind of visualize what's happening here. All right, so there's two things in this paragraph that I think you might be questioning or should be questioning. Okay, does anyone have one of those things? Yeah, Alexander.
Why is counterclockwise positive?
Okay, so she's asked, why is counterclockwise positive? Why is clockwise negative? Did anyone else have that same question? Okay, so I want to show you why. Okay, and you have to start thinking in terms of a coordinate system. So in a coordinate system, if I start here and I move counterclockwise, I'm going this direction, which is in the positive coordinates. If I start here and I move clockwise, I'm going negative. Okay, so that's negative coordinate system. So it's because of the coordinate system. All right, does that make sense? Okay. There was one other spot that I thought we might have a question. Anybody have it? Or anyone have a particular question? Okay, I was thinking of what if you understood what this term rigid means. Did that jump out at anyone or not really? Okay, it just basically means that we're not dealing with fluids here. We're dealing with solid objects that have a defined space, have a defined shape. All right, so we're not dealing with fluid here. We're dealing with solids. Okay, easy enough. All right, the SI unit is a radian. So we're going to start dealing with radians here as a form of angular displacement. Doesn't mean you need to change your calculators to radians. We'll still be in degrees in this class. Okay, but we are going to start working with radians a little bit more. All right, so here's some things that we're going to deal with in our angular or rotational motion. And there's some variables that we need to start picking up. In this particular drawing, okay, the CD is rotating. You guys even remember what CDs are? I'm just kidding. People always ask me that. Okay. So here we're starting at this particular reference point, and it's moving and rotating to this point. Okay, so it's only rotated just a little tiny bit. This is an L, not a 1. Okay, and L stands for distance or arc length that this particular reference point has moved from point A to point B. So if we start here and move up to the top, it's traveled this much distance, okay, which is L. Your book calls it L at least. What would R stand for? Radius. And then this Greek letter is called what? Theta. Good, okay. And theta, it tells us how far that particular thing has rotated in radians. Okay, it tells us the angle, how far it's moved. Okay, so this theta tells us our position at point 2, or if we have a delta theta, it's going to tell us how far we've gone from point A to point B in terms of radians. Okay, so how far around the circle has this thing rotated with respect to where we started. We can connect these three variables using these two equations down here. The angle will be equal to distance over radius, or if you rearrange that equation, you'll get the bottom one. So these two equations mean the same thing. They're just rearranged a little bit. How many of you have heard the term radians, right? You've done this in pre-calc. You understand that an entire revolution or entire rotation of an object is equal to 2 pi radians. Okay? You can look at this depiction here. If something travels one full rotation, its distance traveled would be 2 pi r. What equation does this look like right here? 2 pi r. Circumference of a circle is 2 pi r. So in one complete revolution, its distance traveled is equal to its circumference. Okay, if you take that divided by the radius, that tells us that theta, or the amount of radians traveled in one complete revolution, is equal to 2 pi. So these right here are two conversion factors that we're going to use to get things in terms of radians. Okay, so we know 360 degrees is equal to 2 pi radians, and we know that one complete revolution is equal to 2 pi radians because one complete revolution is 360 degrees. Okay. So let's look at some things some variables that we're going to start dealing with here. What's delta mean always? Change in, or final minus initial. So angular displacement, okay, think of the term angular displacement. It means how far this angle is different from where it started. So that's going to be our delta theta. If we want to look at just where this new position is, or angular position, where it is at this exact point, that's just theta. Okay, it's not final minus initial. If we want to find exactly where something is, it's just going to be that theta angle in radians. Okay, theta is always going to be in radians. Okay, so we've got to convert it to radians now. The big one on this particular one is what we call angular velocity, and it has a new Greek letter called omega. Okay, the computer program draws it a couple different ways. I draw it in a way that's a little different, I guess, than both of those, but omega is like a little W with kind of some wings on it. Okay, this is what the computer's version of omega looks like. Okay, I draw it, it just looks like this. There's little W with some wings on it. Okay, so that's what my omega looks like, and that means angular velocity. So what is its speed with reference to its turning? How many angles is it moving, or what size of angle is it moving per time, kind of, okay? Or how many radians is it moving per time? So this equation right here is for average angular velocity. It's not for an instantaneous little point in time. It's an average. And it's important that we understand every single particle in this rotating object is moving with the same angular velocity. Okay, same angular velocity. Our angular velocity needs to be measured in radians per second. So we're measuring with our angular velocity how quickly that angle is changing, okay, or how quickly this thing is basically spinning or rotating. At what pace that point is changing on the outside. The next one is acceleration. Acceleration also has a Greek character, okay? Its character is called alpha. Okay, it's a lowercase alpha, not an uppercase, if you know the difference. But this is alpha right here. It is different than a regular A, okay? Again, the computer draws it a little bit differently. Mine kind of looks like... this is what my alpha looks like. Okay, that's what, yeah, it kind of looks like a Jesus fish without the tail. Okay, but that's what my alpha looks like. Okay, and I tried to make a distinction in your computer up on this PowerPoint between alpha and the regular A. I'll try and do a better job of pointing that out as we go along. All right, so our acceleration is measured in radians per second squared because our change in angular velocity is radians per second. So this is going to be delta angular velocity, or delta omega, over change in time. All right, so we're still talking about change in velocity over change in time. It's just dealing with angular velocity, how quickly that's rotating. All right. We're going to find a different type of acceleration here as well, okay? So this chapter has 3 different types of accelerations that we need to kind of make distinctions about. And it gives a little bit more of an explanation if you want to look on page 212 about the types of acceleration we're going to be looking at here. Okay, radial acceleration is the centripetal acceleration that we learned about during our circular motion chapter, okay, or A sub r. We're manipulating that centripetal equation to kind of take into account our angular velocity. Okay, so this is our centripetal acceleration that we learned a couple chapters ago. We're manipulating the equation a little bit. You want to walk through the math. It's on page 212, but if you don't, that's fine. Okay, I do want you to look at the picture on page 212 so I can kind of point out what type of acceleration we're looking at. This is a linear. So this acceleration right here, A sub r, will be measured in meters per second squared. Okay, this is not an angular acceleration. This is a type of linear acceleration. Okay, so go ahead and get your book out after you get this written down, and I'll kind of point out what we're talking about here. Okay, if you look at page 212 on the bottom left, there's a rotating wheel. Okay, and the centripetal acceleration is pointing toward the center of the circle. That's our centripetal acceleration, or our radial acceleration, that we learned about in our circular motion chapter. Do we remember that, like, a little bit? Has to point toward the center of the circle. That's what we're looking at here, except now we're going to be able to connect it to our angular velocity, which is a little bit different, okay? But I want you to see the difference between those two, because there's radial acceleration, which points toward the center, and then there's tangential acceleration, which points off at the tangent to the curve, and that's what we're going to look at next, okay? So for radial acceleration, we use this bottom equation. For angular acceleration, we use the top. And for linear acceleration, we're going to use this equation right here. Okay? So now we're going to look at the linear part of it, which a linear motion off of a rotating item is when something goes flying off in a tangent path to the curve. Okay, and you can see that on page 212 again. Okay, so linear motion we can break down and use these three equations. This one we already know, we learned it on our first slide. This is to solve for regular velocity based on an angular velocity, and this is to solve for tangential acceleration based off our alpha. Okay. This velocity equation is what we're going to talk about right now. So this bullet right here has to do with this equation. Okay? This is telling us that although angular velocity, as something is moving, the angular velocity at every single particle in that object is exactly the same. The linear velocity, or the speed at which it would fly off, is different depending on how far away you are from the axis point. Okay? And that's what this equation right here tells us. Okay? So for you to visualize this, think about you standing on a merry-go-round. Okay? You're on the merry-go-round, you're having a blast. If you're closer to the middle of the merry-go-round, do you feel like you're going faster or slower than when you're on the edge of the merry-go-round? Right? If you stand on the edge of the merry-go-round, you feel like you're going so fast you're going to fly off. If you're on the inside, does it feel like you're going that fast? Because when you're closer to the axis point, you have a smaller radius, which means your linear speed or your linear velocity would be smaller. Okay? So if you would fly off the merry-go-round at some point on the edge of the merry-go-round, then you'd go a lot faster than if you flew off and you were in the middle. Okay? Does that make a little bit more sense? Okay, that's the difference here. Depending on how far away you are from your axis point will change your linear speed. It won't change the actual speed at which this thing is rotating. Okay, every little particle of this merry-go-round is moving the exact same speed no matter how far to the inside or the outside they are with their angular velocity. It's the linear or the tangential velocity that will differ depending on the radius. Okay, and that's what this equation right here means. Okay, and then for our acceleration, linear acceleration is this one right here. Sorry. Yeah, okay. This one right here, and it's also called tangential acceleration. And this is the one that is this vector right here. So if at some point you let go or you get knocked off, you're going to still have an acceleration that's flying off tangent to the curve. All right, so we're going to kind of touch up on frequency just a little bit. Frequency means the number of revolutions we can make in 1 second. Okay, so the number of full revolutions or full turns we can make in 1 second. Okay, so we're going to look at relating angular velocity to its frequency using this equation. Okay, we talked about frequency and period back in our circular motion chapter when we used this equation. You won't have to use this really often, but I wanted to give it to you in case your book asks for it or something, just in case you have to convert period to frequency or frequency to angular velocity. But we do use these particular terms, okay? When we talked about frequency before, we talked about it in terms of revolutions per second or revolutions per minute or revolutions per hour or whatever time you want to put with it. But now we need to give it a new name called hertz. Okay, so the unit for frequency is now called hertz, Hz. And we know that 1 revolution per second equals 1 hertz. So this is if I'm given a velocity in RPMs. So let's say that I start out moving 1,000 RPMs and I want to find out what that angular velocity is in radians per second. All right, I'm going to start with 1,000 revolutions per minute. I'm going to need to change revolutions to radians. I'm going to need to change minutes to seconds. So which one would you rather do first?
Minutes to seconds.
All right. I heard minutes to seconds first. So we'll go minutes up top. And then if we want to go from revolutions to radians, what is our conversion factor between revolutions and radians? 2 pi radians equals 1 revolution. Okay, so we'll go ahead and convert that, and then I'll show you the shortcut. What'd you get?
33.3 pi. Do you want it?
4.7.
Try it again. I got about 104 point something. 104 point. Okay. So this is in radians per second. If we're going to convert from RPMs to radians per second, we're always going to have to use this conversion right here. 2 pi over 60. So go ahead and plug in 2 pi over 60 in your calculator. 0.1047 or 0.105, right? Okay, so you can take your RPMs times 0.105 and put it into radians per second that easy. So it's kind of like our kilometers per hour, meters per second shortcut, okay? You can do it by this T-chart every time. You can do it simply with a conversion every time. Doesn't matter, okay? Or you can take it times 0.105 and convert from RPMs to radians per second. All right, so this one tells us a wheel accelerates from rest to 400 RPMs in 20 seconds. What's the angular acceleration? Okay, so our first goal has to be to convert 400 RPMs to radians per second. So that RPM is given to us, that's our angular velocity, but we've got to put it in radians per second. Okay, and this right here, it's a shortcut. It's rounded. So if you do it differently, if you do the entire T-chart, it might be a little bit more exact than what we have. That's okay. Okay, it's going to be off by just maybe a little bit if you do it different ways. That's not a big deal. Okay, so we get about 42 radians per second. What variable will this number go with? What variable should it be? Yeah, the little W looking thing, the omega. Is it going to be our final or our initial? Final. So when it's our final, we leave it off. That means that our initial is what? Yeah, 0, because it starts from rest. Good. And we know our time here is 20 seconds. So now we want to solve for angular acceleration, which is which character? Which Greek letter?
Alpha.
Alpha. Okay, or a little...
Fishy.
Okay. That equation is change in angular velocity or change in omega over change in time. So we're going to plug in final minus initial, which is 42 minus 0 over 20, which means our angular acceleration should come out to be about 2.1, I think. Okay. And what about units here for angular acceleration?
Radians per second squared.
Yeah. Radians per second squared. Your book sometimes labels radians as just R, so R per second squared. I just like to put RAD. Yeah. Let's try this one. What's the linear speed of a child seated 1.2 meters from the center of a steadily rotating merry-go-round that makes 1 complete revolution in 4 seconds? Okay, 1 complete revolution in 4 seconds. So let's go ahead and start listing some variables here. I'll give you a couple seconds to get it written down before we start getting into the math of it. Okay, we could do our revolutions per second if we wanted to. If we know it makes one complete revolution, what do we know that means in radians? It means it makes 2 pi radians worth, right? That means it's 2 pi radians. What variable does that go with? We have an idea?
Is it theta?
Mm-hmm.
Theta?
Okay, so our delta theta here is going to be 2 pi radians because compared to where it started, it made one complete revolution. So it made 2 pi radians worth of rotation. All right, we want to solve here for linear speed. What variable is that we should be solving for? Linear speed. Yep, we're looking for regular V. Okay, that's what our overall goal is here, regular V. Okay, and we know that equation is V equals R times omega. So in order to get to this, our overall goal, we need to find omega, right? So what equation do we have that we can use to solve for our delta theta over delta t? All right. So we get our angular velocity to be about 1.6, 1.5 something? 1.57. And that's going to be in what units?
Radians per second.
Radians per second. Okay. From there, we're going to solve for our linear velocity. So at what speed would it fly off if it were to leave the path? Okay, we're going to take our radius, which is 1.2. Times that 1.57. Okay? Because this is our radius, and we're taking it times our omega. All right, what do we have for our linear velocity?
1.88 meters per second.
Okay, and what's our units for linear velocity?
Meters per second.
Back to meters per second. So when it's our regular V and our regular A, we go back to our normal units. So meters per second. Okay. All right, let's go ahead and try this one on your own. We want to find this particular angular velocity. We're given to us in RPM, so we want to find angular velocity. So this is a simple switch. First and foremost, what needs to happen to the 3 centimeters? Got to go to meters. So you move it 2 decimal places to the left. And then to solve for linear speed, we'll take V equals R times omega. And we'll take our radius times that angular velocity, or omega.